Include the proof of convergence. Okay.
So where PR equals to initial polynomial equals to R minus R1 into R minus R2.
Hmm.
So when we take mode, then how it is greater than equals to, sir?
Ah. Yeah, let me try to recall where it is there. The convergence, right?
Yes, sir.
This one?
Yes, sir.
Hmm.
Sir,
So
P
what
of
is the
R,
problem?
sir, P of R1 plus K mode greater than equals to K
This
plus
step.
greater than equals to plus 2. Yes, sir.
So just a plus b greater than or equals to mod a minus mod b, right? This is true for all real numbers, right?
Okay, sir.
Yeah. So k is a number now, it's a positive number. And R1 minus R2 can be positive or negative, right? So the mod of that is greater than or equals to mod of first one times the first is anyway k is k. Another one is k minus R1 minus R2. Yeah. Any other questions from there? Okay, so I was telling something about the Legendre polynomials, right? So I said this is 1 by 2 power n into factorial n square, or something like that, factorial n, 2 power n into 2 power n into factorial n, right? Times the t power n by dx power n of x square minus 1 power n, right? So I said that this actually satisfies the Legendre equation. So let's see how this can be done. Have you seen the proof of this, any of you?
Yes, sir.
You have seen the proof.
Yes, sir.
Okay. So you want me to do, or if you know that, then I will skip this. And one more, this thing is that Pn at 1 is 1 upon, is just simply 1. Simply 1. Okay, so why is that equals to 1? It is 1 because you look at this, call this as maybe 5. So look at what is Px. This is x square minus 1 for n and nth derivative of this, right? So this is going to be x minus 1 power n to x plus 1 power n. So we are using this notation for the derivative in the bracket. If I write n in the bracket on the top. So when I do this differentiation of the product, product is, this is say f and this is g, and when I integrate, when I differentiate this using the product rule, right? So you have the first derivative is going to be f prime g plus f into g prime, and the second time you are going to get differentiate this, right? So f double prime g plus 2 into f prime g prime plus f into g double prime. So this is the second derivative. So similarly, when I take the n derivatives, we will have f n derivatives times g plus you have the all the terms which has mixed ones, right? That is, these are all the terms which will have the things which f prime also and g prime also, at least minimum one derivative will be there in all these terms. And the last term again you will have f into nth derivative of this. So if I see this for this particular functions, okay, so I will have that is going to be equals to now x minus 1 over n, okay, differentiate this power n times x plus 1 power n. This is one term, okay, that is the term like this, and all other terms will have at least x minus 1, okay, all the terms has x minus 1 as a factor, because all of them will have the derivative of x minus 1 power n at least n minus 1 times, at most n minus 1 times. Therefore, when I take x minus 1 power n and differentiate at most n minus 1 times, x minus 1 will be there as a factor. Okay, so when I take x equals to 1, right, this turns out to be 2 power n, and all these terms are going to be 0 because x minus 1 is a factor. So this is going to be 2 power n, right? This all other terms are going to be 0. Here what you will get, if you see this one, this is again nth degree polynomial. The highest order term is x power n. So that you differentiate n times, I am going to get factorial n. I'm going to get factorial. And again, all other terms in this expansion of this, okay, all other terms in the expansion of this will have again x minus 1 as a factor. Therefore, those things are also going to become 0. So this phi n at 1 is going to be 2 power n into factorial n. Okay, and that factor is divided here. Therefore, Pn at 1 is going to be 1. That is the proof for Pn equals to 1. Pn at 1 is 1. And other one is about the orthogonality. Orthogonality is in the sense that if I take minus 1 to 1, the integral, this is Pnx to Pmx dx. This is going to be 0 when n not equals to n. That is the first thing. And what happens when n equals to n is minus 1 to n Pn square. That is going to be 2 by 2n plus 1. So how do we prove these things? So there is a simple technique to, of course, you have the polynomials. You can do the by directly substituting these things in the equation in this formula, and then try to integrate by parts, and then you can show it. But apart from that, there are some nice techniques coming from the differential equations. So Pn satisfies the Legendre equation. Pn satisfies the equation like this: 1 minus x square into Pn double prime minus 2x into Pn prime, right? And P equals to n, therefore it is going to be plus n into n plus 1. Pn is 0. So this is the Legendre equation. So this equation, we can write this as 1 minus x square, okay, into Pn prime and whole prime. So this is the first two terms, which is equals to minus n into n plus 1 into Pn. Right. So same thing is satisfied for Pm also for Pm. So we have the two equations. One equation is that 1 minus x square into Pn prime whole prime equals to minus n into n plus 1 into Pn, and the same thing for M also. Okay, so when we have this equation, multiply this by Pm, cross multiply this by Pn, okay, and then subtract. Then subtract. So what you will have is on the right hand side, okay, the right hand side you have the m into n plus 1 minus n into n plus 1 into Pn into Pn. Pn into Pn. So you can also integrate from minus 1 to 1. That is the right hand side. So that is going to be equals to, so now you see that this constant here is non-zero. This constant here is non-zero. So the left hand side is going to be the integral minus 1 to 1 minus x square into Pn prime whole prime Pm minus 1 minus x square into Pm prime whole prime into Pn. Okay, so if we show that this is equals to 0, then we are done, because this left hand side, this factor is not 0, therefore you have minus 1 to 1 Pn into Pm. So we have to show that the claim is to show that this is equals to 0. So here apply the integration by parts. When I do the integration by parts, one derivative here extra, it is 1 minus x square into Pn prime into whole prime, that goes on to the second one, right? That is one term. Right? So this is going to be, we are applying the formula, the integral of u dv equals to v u. You will have the one boundary term u into v minus v into d. Right? So let us write this term here. So that is going to be 1 minus x square, right? So this is the derivative and this is v. Therefore, Pn prime to Pn prime. It comes maybe with a minus, but that doesn't matter. It comes in the minus 1 to 1. You can put a minus. And the same term for the second term also will be there. So that will come with 1 minus x square into Pm prime to Pn. So these two terms are the same, so they get cancelled. But there are some boundary terms. What is the boundary term? So here this is this term is the v and this is u. This is u and this is v, right? So u into v, that is Pm into 1 minus x square into Pn prime. So this is at minus 1 and 1. And the same thing for other one. Now you see this these two things get cancelled, right? So these two things are same, so they get cancelled. And this sum of these two terms, you see that Pm at 1 is 0. Therefore, at this point it is going to be 0. And at minus 1, this term is going to be 0. 1 minus x square is going to be 0. So this is this term is equals to 0 and this term is also equals to 0. Therefore, as a whole, this is going to be equals to 0. And since on the right hand side you have the integral minus 1 to 1, this is going to be orthogonal. So that is the first step that we have. Okay. Okay, so now I have to open another file. 100 pages, it closes. So to show the other one, that is integral of Pn square is equals to 2 by n plus 1. So like earlier, let us take the ux to be x square minus 1 over n. Okay, then Pn is going to be 1 by 2 power n to factorial n 2 of ux, nth derivative of x. Okay, so you see that the way it is ux is taken, that is x square minus 1 power n. So when I look at the first derivative of this, when I look at one derivative of this, right? So u prime of x. So this is n into x square minus 1 power n minus 1, okay, times 2x. So this at x equals to 1 or at x equals to minus 1, both are going to be 0. So this is going to be 0 at x equals to 1 and minus 1, both the points, right? So not only that, u double prime also, right? So all the derivatives of this are going to be 0 at x equals to
At x equals to 0 also.
Of course, but we are not bothered about that because our integration is from minus 1 to 1. Right?
Okay.
So this is true up to what case? This is true for k equals to 0. It is true. That is the ux itself, right? K equals to 1 also it is true. And up to what case it is true? Up to n minus 1, right? So this is a power n is there. So if I differentiate n times, right, up to n it will be up to n minus 1, this is going to be 0. So because all of them are going to have x square minus 1 as a factor. Whenever you have x square minus 1 as a factor, then you are going to have this. Okay. Therefore, now you write this minus 1 to 1. Pn square is nothing but 1 by 2 power n into factorial n whole square into this un into un, right? So write u nth derivative of this, again nth derivative of this to dx. Just evaluate this. Of course, Pn square will have this comes twice. So here we apply the integration by parts. So when I do the integration by parts here, okay, so this thing comes with minus 1 to 1, and one of this thing, so one increases the derivative on one and decreases the derivative on the other one. Both functions are the same, and there is a boundary term. So the boundary term is going to be u n x and u n minus 1x minus 1. So we know that n minus 1 times when you differentiate and then take x equals to 1 and minus 1, this term is going to be 0, right? So this term is going to be 0. So this leaves out only the term within the integral. So now you do this integration once again on the same thing, on this term, then you get u n plus 2 and here u n minus 2. So again integration by parts, we will have minus 1 square minus 1 to 1 u n plus 2 into u n minus 2. Okay, and keep doing this how many times? 10 times. Okay, so I will have minus 1 power n minus 1 to 1. This becomes 2n times the derivative times the no derivative here on u. All the n derivatives are transferred to the first function. So now you look at what is u. u is x square minus 1 power n. So what is the highest order term here? Is x power 2n. So this is x power 2n plus other things, right? Plus all other things. So when I differentiate this 2n times, okay, so differentiate this 2n times, I get 2n factorial here, and all of the terms are going to be 0 because they are of lower order. So that is going to be, therefore, from here it's going to be, right, minus 1 power n or 2n factorial to minus 1 to 1. You write this minus 1 power n is there, so you write this as 1 minus x square power n. That is u. Okay, so this integral one can evaluate by taking x equals to sine theta and use the beta functions. Take x equals to sine theta, you get this to be equals to 2n factorial to 2 times 0 to pi by 2 of cos 2n plus 1 theta. So when you substitute these values, you will get all the terms that gets cancelled and you will get the required result. Okay, so this is a beta function. So from the beta functions we can find the value of this integral. Okay, so there is another problem in this. Just wanted to tell that is x power n, or any polynomial can be written as a linear combination of Legendre polynomials of, right? Any polynomial is can be written as is a linear combination of Legendre polynomials. Say any polynomial of order n, if you take, then the Legendre polynomials up to n, up to order n. Why is that? So we know that for n equals to 0, you know that p naught x is 1. P naught x is 1. Similarly, for n equals to 1, p1 x is x. So the polynomials of order 0 and 1 are nothing but the Legendre polynomials. So now assume this for, by induction, assume this for say n minus 1. Okay, that means any polynomial of order n minus 1. Okay, any polynomial of order n minus 1 can be written as, that is, x power n minus 1 is written as alpha naught p naught, like this. Now I have to do this for x power n. I have to do this for x power n. So what is Pn? Pn is a polynomial of degree n, right? It is a polynomial of degree n. So what is that means? That means that it is that is written as x power n plus a n minus 1 x power n minus 1, like this, to n. Therefore, x power n is nothing but Pn minus these things. Now you can write by rearranging the terms, okay, and then this is the nth degree polynomial with the different coefficients. Okay, so if you have any other problems in the tutorial sheet, you can ask me. Any of you, do you have any problems in the tutorials, questions?
Part C of question number 1.
Part C of the question number 1. Can you read what the question is before I open the file?
Find two linearly independent series solution of y double dash plus x square y dash plus x square y equals to 0.
It's a problem only. You can write, no? You can just write the terms.
So while solving this, we are getting a recurrence relation in 3 coefficients. So how do we prove the convergence?
No, convergence you don't have to prove, right? We already proved a big theorem for that, no? Just have to show that the...
Okay, sir. Okay, yes.
So it will follow. From that theorem, the things will follow. But unless you are asked to prove the... in some cases, it is easier to prove from the recurrence relation. So in their cases, you can do. Otherwise, it is convergence. That is why we proved the convergence, right? We proved a theorem for all
Yes.
real analytic solutions. Don't have any other questions?
Yes, sir. Sixth question of tutorials.
That I did now, right now, right? So that there are constants C0, C1, Cn such that for n is...
Sixth, sir. Sixth, not fifth. Find the...
What is that? That might functions.
Yes, sir.
Can you read the question? So I changed it a little bit. What is that? Can you read the question?
Find the weight function wx such that
Okay.
the Hermite polynomial h and x are orthogonal with respect.
See, in the problem 3, we give the Hermite equation, right? So y double prime minus 2x y prime plus 2 alpha y. So 2ny equals to 0. So Hn satisfies this. So now we have to show the, we have to find the weight function so that the integral of Hn(x) into Hny, Hn(x) into Hmx, Wx is 0. Okay. So for that, what I did for the Legendre equation. So recall the Legendre polynomials, right? Legendre equation. So just by writing the equation in the form of a exact equation, right? So these are called self-adjoint forms. So it's basically the self-adjoint forms are something like this: P y prime full prime plus qy equals to 0. So any equation that you have, suppose if there are two solutions, yn and another solution, ym. ym. Okay, so you can put n and here m. So whenever you have some, these are the self-adjoint forms. So you can multiply this equation ym and this by yn. Okay, so when you do that, one term that you will have is nq into yn into ym. Okay, minus m q into of the same thing, and then you can write the integral, whatever the integral, wherever the solutions are valid. Okay, so the Hermite equation, the solutions are holds everywhere. So this one, you can write now the other side also. You will have the p yn prime into yn prime minus p yn prime into ym. So these two things also will get cancelled. Okay. And this equation, now you see that this is going to be yeah. So this is going to be the q into yn into ym into n minus m. Right? So this is n minus m into q into yn into ym. Okay. So this is, so since m is not equals to n, so this is non-zero. This is non-zero. Therefore, somehow you show that the right hand side is 0. Okay, somehow you show that the right hand side is going to be 0. Once if you show that the right hand side is going to be 0, then you have the, so apart from these two terms, there is one more term that you get, that is the boundary terms. So the boundary terms is going to be p yn prime into ym, right? So p yn prime into ym. So on the boundary, I don't know what the boundary is. Right? So, and the other term is going to be y m prime into yn. Okay, at the boundary. So let me write on the boundary. So somehow these things have to become 0. Okay, then you have the orthogonality of the polynomials. Now let's come to this equation. So this equation, I have to write it in the form of in the self-adjoint form. In the self-adjoint. So what is that p? Okay, I should take, so that this equation comes in the form of py prime. Right? So we have, so let us try to find what are the p and q. So we have y double prime minus 2x y prime plus 2ny 0. Now I have to write this in the form of py prime whole prime. So how do I do this? So one way is whatever this minus 2x is there, we can generally write if you have y double prime plus a into y prime plus b into y equals to 0. So only thing I have to write is I have to make this in the form of exact form, right? So what I can do is I can take integral of exponential of integral a into y prime whole prime. So when I do this, what I get? So this is integral of exponential of integral a into y double prime plus y prime will be the same, and exponential of integral a, and integral a's derivative is going to be times y prime. Okay, that means a times y double prime plus ay prime. So that means I look at what is this a and then write exponential of integral of this. Right? Then I multiply by that. So in that a equals to minus 2x. a equals to minus 2x. Therefore, exponential of integral minus 2 to x. So this is going to be minus 2, x is going to be x squared by 2. So this is e power minus x squared. That means I have to multiply this equation by e power minus x squared. So that means what I will have is, when I multiply by e power minus x squared, so exponential of minus x squared to y double prime minus 2x into e power minus x squared into y prime plus, right, e power minus x squared into 2n to y is to 0. So this is the equation which can be written in the form of in the exponential, in the self-additive form, plus e power minus x squared 2n to y is to 0. Now the hn and hm are the polynomials, right? hn and hm. These are the polynomials satisfying the same equation. So just do the same thing what I did earlier. Okay. So you write the two equations, e power minus x squared into hn prime whole prime plus e power minus x squared 2n into hm. So multiply this by hm and do the same thing for hm. Okay, then you subtract and integrate. So what I will have, these terms when I subtract here, I get 2n minus 2m to integral of minus x squared into hn into hm. So take the integral minus infinity to infinity. Okay, this is one, and here you will have the things what I said, the integral of e power minus x squared into hn prime hm prime minus of the same thing. So they get cancelled. So you have the boundary terms. So the boundary terms look like this. The boundary terms on the left hand side, how they look like? Boundary terms on the left hand side looks like e power minus x square into hn prime into hm, right? E power minus x square to hn prime into hm minus infinity to infinity. This is one term. The other one is same thing, hm prime into hm minus infinity and infinity. Now you see that both the terms are going to be 0 because this is a polynomial and this is exponential. Exponential of minus x square as x goes to infinity, you multiply by any polynomial, that is still going to be 0, right? So that is the limit of any polynomial multiplied by e power minus x square as x goes to infinity plus minus infinity is going to be 0. So use that to show that this is 0 and this is also 0. Okay, then what you are left is this term, and all other things are 0. For n not equals to m, you get this to be 0. Therefore, wx is going to be e power minus x squared. Okay, you can do this for other problems.
Yes.
Problem 9,
Yes,
which
sir.
you can do, you can try to do for problem 9 what it is, Lagrange's equation. And also the Chebyshev equation. What are the weights which for which these are polynomials are orthogonal? Problem 12 is the similar, but you have to do carefully. Try to do it. Okay. Any other questions?
Sir,
Hmm. Who is this person? Himanshu Panwar. Is there now? Himanshu Panwar. Is there online?
Yes, sir.
So what is your question? Could you help us by giving examples of questions that are generally asked regarding the topics we are covering? You mean that I should give some important questions for the exam so that you score the marks?
Not like that, sir, but yeah, that will also help us in scoring in exam.
For this kind of questions, my answer is the same. There
But
is a
but
university called Indira Gandhi National University, National Open University. Okay. So that will really help you to score the marks. IIT is not a place for such kind of things. I am giving you 17 problems and you are asking, I am discussing these 17 problems in the tutorials and you are asking, give me important questions for the exam so that I can score. That shows your motivation level for doing a master's program. That too from IIT. I should give 5, maybe I will ask 5 questions in the exam. So you read these 10 questions and practice these 10 questions very well. And then out of the 10 questions, I'll give 5 questions in the exam. This is what you want, right?